Huh?
Some of them are from way back to 2 points.
Oh, well, good. Yeah, so we're going to review that. All right, so as you can see on
I have the worksheet. I just can't remember.
your practice final exam is how many pages? Oh, well, there we go. I have it right here. It's 20 pages, but that's really 10 front and back, right? And the final exam is 4 pages front and back. So the practice final is actually, well, let's see here, 9 pages front and back because the 10th page is just an answer key. So it's 9 pages front and back, and then the final exam is 4 pages front and back. So we're practicing more problems than will be on the final, which is probably a given. So the first 10 pages are all about derivatives. That's my goal to do today. And then the second 4 pages, or the second 8 pages, I guess, is all about integrals, and that's what we'll do on Thursday. Because as I said at the very beginning of the semester, I hoped to give us 2 days to review for your final exam, and indeed we do. So we'll review all day today on derivatives, and we'll review all day Thursday on integrals. And then next week you'll take your final exam on Tuesday. Is that Tuesday the 12th or Thursday the 12th?
Tuesday. Because my son's birthday is
Oh yeah, that's right, Tuesday the 12th, yep. All right.
We're taking our final exam on Tuesday, so we don't have to show up on Thursday? No.
We're not scheduled for Thursday. If you'd like to be here, I could come here and we can all sing songs and. All right. Well, let's go ahead and start with the beginning of the packet, and I put that note up there at the top so you know where the derivatives were, where the integrals are, and where the answer keys are. Okay. So find the domain and range of the function graph below. Use interval notation. So how do we use interval notation to express the domain and range of that?
Isn't it like -1 and 3?
Yeah, well, let's write down the definitions. Definitions are very helpful. So we'll start with the definition. The definition of domain is how far the graph goes from left to right. And I use brackets. They could be parentheses. Remember, brackets are not in, I'm sorry. A closed circle is the same as a bracket, while an open circle is the same as parenthesis, which is used for infinity. So that's kind of your key there. So what's the domain for this graph? How far does it go left or right?
I have bracket -1 and then 3 with an open with a non-bracket.
Yeah, that's exactly right. -1 to 3 with a bracket on the left and a parenthesis on the right. So that's how far it goes left and right along the x-axis. That's what we're really saying when we say domain. We're talking about along the x-axis, where does the graph exist? Because those are all the potential inputs. So then, what's the definition of range? To keep in mind what the definition of range is, the domain goes left to right. That means you're going from the negative side of the spectrum to the positive side of the spectrum. And range works the same way. So you're going from down to up. How far down does it go, the negative end of the spectrum? How far up does it go on the positive end of the spectrum? So how far down to up does it go along the y-axis?
4.
How far down?
-5.
And how far up? 4. So it goes down to -5, but is that a parenthesis or a bracket?
The 4.
Yeah, parenthesis for -5, because it goes down, but it doesn't touch -5. And all the way up to 4, and what is 4, a bracket or a parenthesis?
Bracket.
Bracket. Because it does, in fact, reach 4. There's a point up there at the top. Well, that's just a review of interval notation. If we wanted to right now, we could ask a similar question and say, when is the derivative positive? And the derivative is positive just right here on this portion, right? Because the slope is increasing. So I could say the derivative is positive on the interval from from -1 to 0. That's where the derivative is positive, just that little bit. Why don't I include 0? Is the derivative positive at the top? No, the derivative is 0 at the top. So the derivative is positive there, and the derivative is negative over here. So that would be from 0 all the way to 3. That's just an example of how you would use interval notation. You use interval notation to describe different properties of the graph. All right, well, moving on. That's just a little review of domain range.
I was going to say, you're not going to ask us that, right? Not in this.
Not in that particular question, no. Okay, you can see the numbers go out of order because I just picked and choose which problems I felt were very key. So number 7, a vehicle purchased for $25,000 depreciates at a constant rate of 9% per year. So if you just kind of imagined that, what would our graph look like? You'd start at 25,000, and then the vehicle starts to depreciate. And what's going to happen in the long run? The value of the vehicle goes to zero. Right? It'll be worthless. It'll be a worthless piece of trash in the long run. All right, so it starts depreciating, and it's depreciating at a constant rate of 9%. So we know that our R value is what?
9.
Yeah, 0.09. And we just want to find the value at that, 10 years from now. So you have two different formulas to choose from when you think about compounded interest or continuous interest. This is continuous interest, at least I believe so. Yeah, it's continuous depreciation. So if it were discrete, you would use the formula A equals P 1 plus R over N to the NT. I don't think we use that formula for anything in this class. That's discrete interest compounding. If it's continuous, or in this problem it says constant, then you use the A equals PERT, PE to the RT. Oh, by the way, these questions are out of the review of chapter 1. This is chapter 1, the overall review. So how do we plug all of our information in? How much will the vehicle be worth?
Isn't A the 25,000? Sorry, P the 25,000?
Yeah, P is the 25,000. That's the principal. That's how much it was worth originally. And then E to the
0.09 times 10.
It is definitely 0.09, but is it 0.09 positive or negative?
Isn't it positive?
Well, this is depreciation,
Oh, negative.
so it's going to be negative. Yeah, this is depreciation. And that's it. You type that into your calculator, and that's going to tell you how much the vehicle is worth over time. True check. 25,000 e to the negative 0.09 times 10. Did you all get $10,000?
10,165.
Yeah. Now, how could we check that real quick? Like, just as a rough check. If you're losing 9% per year, how much value are you keeping each year? If you're losing 9% of the value, how much value do you keep? 91%. So we could take 25,000 and multiply by 0.91, and that will be how much value I still have after the first year. I hit enter, and then I hit times 0.91 again, hit enter. That's how much value I have after the second year. And then 3, 4, 5, 6, 7, 8, 9, 10. At the end of 10 years, according to this model, I would have $9,735 left. But that was only if I take away the 9% value at the end of each year. This was continuous depreciation. And so it's slightly different, but we're in the ballpark, right? So we know that our answer is very reasonable. Okay, well, that's it. So definitely you're going to see this type of formula in the calculus problems as well, e to the, taking the derivative of e to the. All right, now, why is that not very big? Can everybody see that? Okay. All right, folks, any questions there? Okay. Now, I probably have to speed things up a little bit, but I do want to make sure that everybody's questions get answered. So by all means, please, raise your hand, let me know what your question is. Now let's keep going. And number 8, we're talking about a bank featuring a savings account with an annual percentage rate of 3% with interest compounded quarterly. Oh, well, here's a compounded, a discrete problem. So we will use that formula at least once. A equals P 1 plus R over N to the NT. So how do we plug all of our information in now?
A equals 8,000. 1 plus 0.03 over quarterly, which is a 4, right?
Yeah, quarterly is 4. N is the number of times you compound.
And then 0.03 times 4.
What's that? The NT, that's 4 times how many years? So how many years are we waiting?
8.
Yeah, 8 years.
Oh, okay, never mind.
Yeah, but you got it. So that would be the compounded discretely. So you're only compounding interest so many times a year.
If I read the instructions.
Yeah. All right, well, so we can go ahead and calculate that. That'd be 0.03 divided by 4 plus the 1 to the power of 32, all times 8,000. So I got 10,160.89. Now, that's just how to use the compounded discretely formula. The next question is really interesting. It says, what's the annual percentage yield? The annual percentage yield, the effective annual percentage rate, which includes all the compounding in the year. So for instance, they're compounding the interest 4 times, but we're 4 times per year. But we're asking, what about the APY? Do you guys know that phrase, APY? It's on every credit card statement that you get and on loan statements that you get. APY says the annual percentage yield. It says, even though you're compounding your interest quarterly or 12 times a year or how many times you're compounding your interest, what if you just pretend that you're only compounding it once? What's the effective amount of interest you're getting that year? So everyone, let's compare 2 quantities. Let's do 1 year's worth of interest. All right, so that would be 8,000 times 1 plus 0.03 over 4 to the 4 times 1. All right, so that's our 3% interest compounded 4 times, but we're only going to do it for 1 year. And let's calculate how much actual interest we get from those 4 compoundings. So you type all that in your calculator, 0.03 divided by 4 plus 1 to the power of 4 times 8,000. And that gives me 8,242.71. So that's how much interest you got from compounding it 4 times. Well, what's the effective annual interest rate? What interest rate would that be if you were only getting the interest once? So how do we calculate that? That would be, say, 8,000 times what interest rate would give me 8,242.71. So if we're just claiming that we're just going to multiply it by a single interest rate. So how do we solve for
Do we have to divide by the 8?
Yeah, we're just gonna divide off the 8,000. And this is going to tell us effectively what interest rate we're getting for the year. So I take that, divide by 8,000, and that's 1.03033391. So what interest rate is that? If you move the decimal twice, that's 3.03%. So it's slightly more. That's effectively the same thing. So what they're saying is you could either do 3% compounded 4 times, or you could do 3.03% compounded once. And that's what APY stands for. APY, the annual percentage yield, is you're just saying, hey, look, forget all this compounding business. I don't care about you compounding the interest quarterly 4 times a year. Just tell me how much money I'm getting at the end of the year. And so the APY is the effective annual interest rate. And both of these are totally equivalent. The only difference is that with compounding it 4 times, your account actually goes up in value 4 times that year. Whereas with the APY, your account would only get that interest once at the end of the year. Okay, well, we never talked about APY in this class, but it's a good business application, and I thought that was a pretty nice question. So how do you solve for the APY? How do you solve for APY? You calculate the amount of interest you get from 1 year of compounded interest, and then just divide by the 8,000 principal, and that will tell you what interest rate you are effectively multiplying by once for the year. Okay, everybody who just got here, like Mong and Carmen and David, you all picked up a practice final over there and you're all with us now? Okay. All right, well, let's keep going. Number 9, use the graph of F to evaluate the average rate of change. How do we calculate the average rate of change? So now we're starting with some calculus concepts. Nick, did you just have a heart attack or heartburn? What happened?
Yeah.
Yeah. Okay. It hurt a little bit. Talking about the average rate of change? Oh, that happens. So how do we calculate average rate of change? Everyone remember, what is average rate of change? Remember when we started talking about calculus, we talked about two ideas. Here, I'm just going to draw a graph. You could either calculate the slope from one point to another point, or you could calculate the slope at exactly one point. Yes, secant and tangent slope. So this is a secant slope, and this is a tangent slope. This is a good note to take down. The secant slope is the average rate of change, which literally is just what we refer to as slope. Had they said, use the graph to find the slope, okay, that's literally all that means. It's the secant slope. Just find the slope between the points from 1 to 3. So here's the point at x equals 1, and here's the point at x equals 3. And so when they say they want the average change, what are we going to calculate? Literally just the slope between those 2 points. So that wasn't as bad, right, Nick?
No.
Not so bad at all. Okay, good. All right, whereas since that's the average rate of change, the tangent is the instantaneous rate of change, which is what calculus told us, right? So the tangent slope is calculus, and the secant slope is pre-calculus. That's the difference between those two. Now, you've got some options here for calculating the slope. Literally, can't you just visually calculate the slope? We could probably just literally calculate the slope visually. How far do we go down? We go down 1, 2, 3, 4. Then we go to the right, 2. So remembering the definition of slope, slope is the change in y over the change in x, which I always like to call the up-down over the right-left. Or you can use the official formula of y2 minus y1 over x2 minus x1. Either way, since we have a graph, we could just conceptually say that we're going down 4, right 2. So that's down 4, right 2. And the answer is down 2, right 1. So the average rate of change is down 2, right 1. That's the slope between those 2 coordinates. Is that an acceptable answer on a final exam to do it visually? Yeah, that's the definition. That's the definition of slope. If you wanted to, could you write out the coordinates like 1, 5 and 3, 1 and actually calculate slope? Like 5 minus 1 and 1 minus 3, which is 4 over negative 2, which is negative 2 over 1. Could you do it that way? Sure, you can do it that way too. I think the main point of problem number 9 is to show you what life was like before calculus. Before calculus and Newton and Leibniz, all they were able to do was average rates of change. And you can imagine these mathematicians back in the 1500s who didn't have calculators, they would just start making those intervals shorter and shorter and shorter. They're like, well, what's the average change from here to here? Or what's the average change from here to here? And so it became very natural for them to think, well, what's the average change over an infinitely small interval? And so that was a natural progression for them to think about. Okay, any questions about number 9? Let's keep going. By the way, that was it. There were only 8 questions on the practice final from chapter 1. So those were the main ideas from chapter 1 that are useful in calculus, specifically with what we did. So now we're talking about chapter 2. And in chapter 2, we're talking a lot about slope, and we were talking about limits. So remember, going all the way back to limits, number 10, you might just want to write it down. It's about limits. You might be thinking, I've reached my limit. No, that's not what we're talking about. So remember, in limits, we had a couple ideas. And that was that a limit is wherever your fingers touch, provided there's a point in the middle of it. And that you can approach a limit from the left, and that you can approach a limit from the right. So you'll notice in this graph, there's definitely something funky happening at the x value of -1. So at the x value of -1, there's something funky happening where what we approach from the left is different from what we approach from the right, which is different from what it actually is at the value of x equals -1. And this is why we have so many different ways of talking about it. What's this first one asking? The limit as x approaches -1 with a negative sign. What's that extra negative sign mean? You know, from the left. So we're saying, what's the limit as you approach -1 from the left? So what is the limit? as you approach from the left. And remember, the limit, we're always asking for a y value, the y coordinate. What's the y coordinate as we approach from the left? Yeah, -3. Yeah, limits are asking for the y value. Put the function value. So what about this next one? It says the limit as x approaches -1 with a positive sign. What does that mean? Positive sign on the right of it. It means we're approaching -1 from the right. And so what is the y value we're approaching from the right? Yeah, from the right-hand side, we're approaching -1 on the y value. So that's a -1. Now, what if you say the limit as x approaches -1, but you don't specify that you're approaching it from the right or the left? What does that imply that you're doing? You're approaching it from both directions simultaneously, and the limit only exists if your fingers touch. If your fingers don't touch because you're approaching an asymptote, or, well, if they just don't touch, then there is no limit. You say it does not exist. But if your fingers do approach, then the limit does exist. In this case, what happens as we approach from right and left simultaneously? They don't touch. So you would say the limit as x approaches -1 of f of x does not exist. Because your fingers don't approach the same value simultaneously. And finally, what is the value of f of -1? If I plug -1 into this function, what value does it calculate? Yeah, it actually calculates the value of 1. That's why there's a little dot up there. So f of -1 is equal to 1.
He says D&E because they don't touch each other?
Yeah, D&E because they don't touch each other. Yeah, fingers must touch. That's a nice note for right there. Thanks, Julie. Fingers must touch. Now, that's actually a really good reminder of the 3 rules that a function must meet in order to be continuous. I'm just going to look ahead real quick. To be continuous, and we'll see this in a second, but I thought we'd look right now. To be continuous, remember that the function has to be defined, continuous at x equals a. For a function to be continuous at some value, f of a has to actually exist. Right? So there is actually a value. If you plug it into the function, it will actually compute a value. Next, the limit as you approach a from the right and the left has to exist as well. So your fingers have to touch. And finally, the limit of x approaches a of f of x actually is equal to that value that f of a actually computes. So that was our definition of continuity. So f of a exists means there's a point on the graph at x equals a. And the limit exists, meaning your fingers approach each other, or your fingers touch. And the point on the graph is actually where your fingers touch. Yeah, so that's just a little preview. I think that went very well with that question, so I went ahead and talked about it. So in this particular case, this graph is not continuous at -1. Actually, which of those does it fail? Which of these 3 criteria does this graph fail at the x value of -1? First of all, does f of -1 exist? Yeah, it does actually exist. There's a point on the graph at x equals -1. So that one's fine. It passes that. But does the limit exist? Do my fingers touch? No. So that's it fails. And then what about, is the point on the graph the same as where your fingers touch? No, because your fingers don't even touch. So this graph fails to be continuous at x equals -1 because it fails those 2 criteria. Okay, we'll see another question just like that in a second. Okay, so what were some times when a graph could fail to be continuous? We've got one right here. The graph just doesn't even match up. But what was another time that a graph would not be continuous? So let's make a little note over here below this question. Not continuous if. What would those graphs look like if they're not continuous? Or just from your own conceptual idea of continuity, you have to draw your pencil and your graph smoothly. So what would break up a continuous graph? What? It's something like this, right? They don't even match up. But what else could it be?
A cusp?
A cusp is continuous. My pencil didn't leave the paper. That's non-differentiable.
We have a line, we have breaks in it.
Yeah, simply a hole. Right? So that would be one option, a hole. This is maybe a break. What else? What's another time it's not continuous?
There's no.
There's one more classic one we talked a lot about. When the graph, an asymptote. So those are three pretty good times where something is not continuous. A break, a hole, or an asymptote. All three of these fail the definition of continuity for one of those three reasons. You know, either there's no value at x equals a, or the limit didn't exist, or the limit wasn't the same as the value of f of a. So in this particular problem, number 11, does this limit exist? What happens when x approaches 6? So for instance, if I just take this rational expression and I plug 6 into it, what do we get? In the numerator, -5 times 6 is -30, plus 30 is 0. And in the denominator, 6 squared is 36, minus 30, minus 6 is also 0. So 0 divided by 0 is undefined. So we cannot simply plug in 6. Who remembers what we have to do? You have to break it down, factoring. We have to factor it. So in the top, can we factor anything? Yeah, we can take a 5 out, so -5 outside of x minus 6. And on the bottom, can we factor?
Yeah.
Yeah, what multiplies to make 6? -6, that would add to make -5. Yeah, 6 and 1. So this is going to be x minus 6 and x minus 1. So there, we factored it. And exactly. Then you can cancel out the x minus 6, which is a good thing because that was the reason why our expression was undefined, because we were plugging in 6. And if you plug 6 in, both of those terms become 0, which made the whole thing 0 over 0. But now that we canceled it, we have -5 over x minus 1. And now we can plug in 6. And that gives us -5 over 6 minus 1 is 5, which is simply -1. So the limit of this rational function is actually -1. The graph approaches -1.
We need to write approaches next to it like last time.
Oh, no, you don't have to. That's implied by the word limit. The fact that there's a limit symbol here, they're saying, what is the limit? The limit is -1. Now, what is actually happening in this graph, though? Is it a break? Is it a hole? Or is it an asymptote? It is a hole. Why are you saying it's a hole?
Because you said that if it crosses a top and the bottom cross out, then there's a hole.
Exactly. Anything you cross out of the top and bottom is a hole. What about this other term? The x minus 1 didn't cancel out of the bottom. Therefore, that represents an asymptote. What you do is you look at the denominator, okay, the denominator of your expression. You don't want either of those things to equal 0. You don't want either of them to equal 0. And this one canceled out, so that's just a hole. This one, x still can't be 1, and so that there's actually an asymptote there. And of course, I want you to see that. So what are we going to do?
Graph it.
Graph it. So here's my graph of -5x plus 30 divided by x squared minus 5x minus 6. And take a look at this graph. First of all, where's the asymptote? Is there an asymptote at x equals -1? Wait, can you guys see that? You can't see that. There. Is there an asymptote at x equals -1? Yes, the asymptote is there. It's kind of tough. Well, geez. So we've got an asymptote, and is there a hole? Where should the hole be? At 6? Let's look. Oh, goody, there is a hole. Oh, there it is. So there really was a hole in the graph at x equals 6. And there really is an asymptote at x equals -1. So make a note to remind yourself that when you're given an expression to take a limit, if the term cancels out, that represented a whole. And if the term doesn't cancel out, that represents an asymptote. And in any case, what we're trying to do is cancel out those factors so that you can, in fact, plug in 6 and actually get the limit. Oh, and by the way, what was the limit? As x approaches 6, what's the value around? The value is, wait a minute, what am I approaching? 6? 6? It should be -1. What did I do wrong? -5x plus 30, x squared minus 5x minus 6.
Did you put plus 30 or?
I wrote
Oh,
-5x plus 30. Well, that's strange. We got a different limit. They're saying the limit is around 0.7 something. Did we calculate something wrong?
Is this
Can it
something
be
like
3 and
x
2?
is supposed to be x minus 6? Because the middle term is a -5.
Which one, Mom?
That one, yeah.
Yeah, that would be x minus 6, -5x plus 30, and then x squared minus 6x. Oh, that's a +1. +1. I factored that wrong. Folks, I'm so sorry. That's x minus 6, x plus 1. So that's +1, and 6 plus 1 is 7, and -5/7. That's our limit. Oh my goodness. I wonder what 5 divided by 7 is. 5 divided by 7 is -0.7142, and that is in fact what the line was approaching. Negative. Negative, right? Yeah, -5/7. And sure enough, look at the graph. Is that where the hole is? Yeah. Yeah, so it was approaching -5/7. Whew. Boy, see, good thing we thought about it and checked about it, you know? Verifying that it actually worked by looking at the graph. Okay, moving on. So number 12, that is very similar to what we just discussed. Why does this graph fail to be continuous at x equals, what does it say? X equals 2? Yeah. First of all, folks, is the graph continuous at x equals 2? No, because there's a hole there, right? We definitely know it's not continuous. There's a hole there. If I was tracing this with my pencil, I'd have to pick up my pencil and start again. So it's not continuous. But why is it specifically not continuous? So go in order. Is f of 2 defined? What is the value of f of 2? If I plug 2 into this function, what's the output? There isn't one. There's no point anywhere located at the value of x equals 2. So that's actually undefined. There is no value for f of 2. So definitely it failed that criteria. There is no actual point at the x value of 2. What about the limit? Does the limit exist? Do our fingers approach? Yeah, our fingers do approach. Where do they approach? What y value? The -1. So indeed, it does exist. The limit as x approaches 2 of f of x equals -1. So the limit did exist. But does the value of that limit, which is -1, equal the value of the function, which is undefined? No. So folks, if there's a question like this on the final exam, I would like you to give some indication of each of those as to why it is or isn't. So, you know, it's one thing to put a frowny face and a smiley face and a frowny face to let me know that it failed the first and last one. But I'd like you to actually tell me specifically. So was I clear enough on those? That for the first one, you would say f of 2 is not defined. There's no point on the graph. There is no point on the graph. For x equals 2. And then for the second one, the limit does exist because your fingers touched. My fingers touched. Whereas this last one fails because the point where my fingers touched is not equal to the point that the function equals because the function is not equal to anything. So -1 is not the same value as undefined. What do we need now? Rose and Thomas? I wonder if they're coming today. Yeah, Rose and Thomas. All right, any questions about the definitions of continuity? Does this all ring a bell? Do you remember months ago when we were first doing this? Hopefully this is a nice refresher. Okay, so number 14 is going back to the idea of domain and range, but they're not asking for the full domain and range. They're just asking for the intervals where the derivative is positive or negative. So why don't we do the first one first? The derivative is positive when? So trace on your graph where the derivative is positive. That part, right? The derivative is positive between what and what?
-1 and 1.5.
Yeah, do you think it's -1 to 1.5?
It looks like 2.
Really? Does it look like 2?
Oh,
I don't know. I think -1 to 1.5. Now, is it -1 to 1.5 with parentheses, or is it -1 to 1.5 with brackets?
I think that's a 2.
Why parentheses? Because what? We're saying when is the derivative positive, that means the graph has to be sloped up. What is the slope at the very bottom? 0. And what's the slope at the very top? Yeah, so those 2 points are not included in when the derivative is positive. So we definitely don't include the endpoints, and that's why it's not brackets. It's parentheses because we're not including the very bottom or we're not including the very top. All right, so when is the graph negative? Oh, sorry. When is the derivative negative?
-infinity to -1.
Yeah, from -infinity to -1.
And 1.5 to infinity.
Yeah. And folks, notice that you use the union symbol. That U right there means union. So it means or. It means either from -infinity to -1 or from 1.5 to infinity. And that's using the same interval notation you would use to talk about domain and range. Okay. This next question is a business application. What did I say? The total cost in dollars to produce how many units? Q units of a good is given by that function. So we have C of Q equals 5.8 Q plus 41,000. Folks, what does that function mean? The cost of Q units is 5.8 Q plus 41,000. What do those two numbers represent? What does the 41,000 represent? Yeah, that's your fixed cost. Like, that's probably the money you paid to buy your machines, your shop, your location. What is the 5.8 Q? Sorry, what's the 5.8? Yeah, that's your variable cost. That's just the cost of the supplies you need to literally make that one item. So you've got your fixed cost, your variable cost. So the first question, question A, what's the total cost to produce 9,400 units? What would you do?
Just plug the 94 for the Q.
You just plug it right in. So the cost of 9,400 units is 5.8 times 9,400 plus the 41,000 fixed cost.
95,520.
What did you get?
95,520.
95,520. Yep, that's the total cost to produce all 9,400 of them. The second question brings in the calculus idea. It says, what's the cost of the 9,401st item? And what do we call that when you just want the cost of one item? Yeah, that's what it actually is. The traditional method of defining that would be the cost of the 9,401 items minus the cost of 9,400 items. Yeah, because that way you're zeroing in on just the cost of that 9,401st item. That's the traditional definition. And by traditional, we should also say accurate. That literally is the cost of the 9,401st item. And what do we call that? There's a word for that.
The marginal?
The marginal cost. Yeah. This is the marginal cost. So when you're just looking at the cost of one item, that's called the marginal. On the margin, marginal cost. So you've got a couple options there. You could go ahead and plug in 9401 into the function and calculate both of those, which is not a bad idea at all. You could do that. You could just go ahead and see, we already did the 9400 one, so that's 95520. And so now we go ahead and do the other one, 5.8 times 9401 plus 41,000. So that one was 95525.8. And then you subtract the two, and you get 5.8. So apparently it's $5.80 for that one item. Why is that answer obvious?
Because that's the 5.8 variable.
Yeah, because that's the variable cost. So that's obvious. You know, that one item, it only had that one variable cost. So since the fixed cost was already a sunk cost, just that one item was 580. Now the other way you might have seen that is if you actually wrote out cost of 9401 minus cost of 9400 and plug that in, you'd have 5.8 times 9401 plus 41,000 minus parenthesis 5.8 times 9400 plus 41,000. And what happens to the 41,000s?
Cancel.
Yeah, they cancel out because you're going to subtract both of those. So the 41,000s cancel. And now I have 5.8 times 9401 minus 5.8 times 9400. And what can you do? Mathematically, they're both being multiplied by a 5.8. So you can factor that out, and you get 9401 minus 9400. And that's how you get 5.8 times 1, which is the 5.8. So that's why that works out. That's why that works out, that when you look at the marginal cost of a linear cost function, the marginal cost is simply the variable cost. Would that have worked out had our cost function been quadratic? If the cost for something was 5.8 q squared plus 3q plus 41,000? Would then it have been fair to just assume that it would be 5.8? Yeah, then we wouldn't be able to do that because, you know, the 41,000 would still cancel out, but you'd have a q squared term and a q term, and you couldn't just jump to that conclusion. You would have to actually calculate it and see what you get. Okay, so that's the traditional and accurate way of finding the marginal cost. What's the calculus way? What's the definition of marginal for any function? If the cost function is 5.8q plus 41,000, go and write that down. So we've got our traditional method right here. Now we've got our calculus method. How do you find marginal cost? You take the derivative. So c prime of q, and the derivative of 5.8q is 5.8, and the derivative of 41,000 is 0, and then that's it. So the marginal cost, this is the marginal cost. And so the marginal cost of the 9,401st item is still just 5.8, because there's nowhere in this formula, the formula is a constant. So you can't plug 9401 anywhere in, it's just answer 5.8. Now in this particular case, what do you notice about the traditional marginal cost and the calculus marginal cost? They are actually the same. But that's only because our cost function was linear. Had I had this function, like a quadratic function or maybe an exponential function or maybe a rational function, that wouldn't have been the case. So the traditional one is accurate. The calculus method is approximate. Even though this time it actually gave us the same answer, I would want you to know that the calculus method of taking the derivative of the function, that's just an approximation. It's just a close approximation. All right, got it? How about this one? Let the demand function for the product be given by the function d of q equals 1.25 q plus 290. where Q is the quantity of items in demand, and D of Q is the price per item that can be charged when Q units are sold. What does this tell us again? Everyone, what does D of Q represent? Q we know. Q is the quantity. What is the demand function actually telling us? It has the letter D, which stands for demand, but it actually represents something different. D is the, D actually represents the price per item. So that's very important that you note that and memorize that. D is the price that you're going to sell that item for. So that's the price. So let's go ahead and answer the first question. Now, I broke this into two questions, folks. I want the regular revenue and I want the marginal revenue. So first of all, just what's the regular revenue? What is our revenue? So I'm going to write R of X. The revenue is what? Oh, not X, Q. Q is for the quantity, right? So what is revenue? Is what? Revenue is how much money you're going to bring in, right? And so it's the price times the quantity. That's how you would calculate revenue. You say, okay, well, this is the price that I'm charging for each item. This is the quantity of how many items I just sold, and that's my total revenue. So what is my R of Q function? What is the price? What's the formula for price? Yeah, the 1.25Q plus 290. And how many are we going to sell?
Negative 1.25.
Oh, that is a negative. Thank you. And the quantity is Q. So our revenue function is the price times Q. If you wanted to, you could even write that down as a formula. It's D of Q times Q. In general, that's how you calculate your revenue. So what's our final formula? Negative 1.25 Q squared plus 290 Q. I think I was a little ambitious with space. I'm already running out of space, and I haven't answered the first question yet. So what's our revenue from selling 228 items? That's what my verbiage here isn't the best. I want the regular revenue from selling 228 items, and I want the marginal revenue from selling the 228th item. So what's our revenue from selling 228 items? How do you find it? How do we find the revenue? You just plug it in. So negative 1.25 times squared plus 290 times 228. And the revenue is $1,140. So that's the regular revenue for selling 228 items. You know, something we lost there is we don't actually know how much we were charging per item. How can I find out now pretty quickly? What was my cost per item? Since I brought in $1,140 and I sold 228 items, how much did I charge per item? Yeah, you can divide by 228, and yeah, the answer was $5. So this was $1,140, which is $5 per item. That's theoretically how much we were charging per item, but that's on average, right? That's $5 per item on average. That's the average $5 revenue per item. And in fact, that's what you'd get if you plugged in negative 1.25 Q plus 290. That would be, right, negative 1.25 times 228 plus 290. Yeah, that was the $5. So that was the cost. But now what I'd like to do is get the marginal revenue. What's the marginal revenue of the 228th item? So now how do we get marginal revenue? You take the derivative of revenue, So what's the derivative of negative 1.25 q squared plus 290q? Yeah, so we bring down the 2 and multiply, so that's negative 2.5q plus 290. That's the derivative of our revenue function. So now we've taken the derivative. This is going to be marginal revenue. And we would like to find the marginal revenue of the 228th item. So how much revenue did I actually bring in from the 228th item? Not on average, because this is telling us our average revenue per item. This is going to be the actual revenue for the 228th item. So you plug it in, negative 2.5 times 228 plus 290. Ooh, did I do that right?
Yeah, I got it.
My goodness, I did. Yeah, so what was the actual revenue from that item? Yeah, negative 280. I lost a lot of money from actually selling that 228th item. I was losing money. Now, how does that even make sense? We already know that on average, we're bringing in a revenue of $5 per item. But we're saying that the revenue from the 228th item is negative. Well, first of all, what's the shape of this curve? Since it's q squared, but it's negative, what shape is it?
U-shape.
Yeah, it's a U shape, but it's upside down. So where then is where's the 228th item? Is it here? Or is it way over here? Where the revenue function already went down. So that is why that marginal revenue is negative. Let's just take a look at it real quick. That was what now? Negative 1.25 x squared and then plus 290x. Oh yeah, see, look, this is sad. There's our parabola, which you can't really see. The parabola goes really far up. Let me change that real quick so we can actually see it. How far up does it go? Whoa, more than 2,000? More than that? Aha, there's our parabola. And where's the value 228? Oh, well, actually, where is the value of 228? 228 is right there. Okay, so we're saying that at that moment, the 228th item has a revenue of what? No, at 228, what's the revenue? 1,100? Is that what we thought? 1,100? So it is. But notice that the revenue has been going down for quite some time, meaning that past the maximum revenue, every item that you bring in, you're bringing in less money than the previous one. And so for that particular item, it actually brought revenue down. Okay. Well, folks, the process we just did for revenue, we're going to duplicate that process and now do it for cost. So let's consider both. Here, so I can see. So find the regular and marginal cost to produce 228 items or the 228th item. So what's our cost function? We didn't read that far yet. Suppose the fixed cost of production are $6,000 and the variable costs are $5. So what's our cost function? Oops, C of Q. We're going to use Q again. The costs are what? What's our formula for cost? It's fixed cost of $6,000 and variable cost of $5. So what's our cost function?
5Q plus 6,000.
Yeah, 5Q plus 6,000. That's our cost. That's the fixed cost. That's the variable cost. That's our cost. So we can now go ahead and find the cost of 228 items. So the cost of 228 items, of all 228 items, is 5 times 228 plus 6,000. That's the cost of all 228 items, 7,140. Why are we very, very sad if this is our business? What was the revenue from 228 items?
140.
Yeah, only 1,000. And our cost for 220 items is 7,000. Is this a good business? This is a terrible business. We all want to leave our partners right now, right? Okay, so, but what now was the cost of the 228th item? So now take the derivative of cost, and that's our marginal cost. The marginal cost of just the 228th item. What's the derivative of 5Q plus 6,000? Yeah, just 5. So the marginal cost of just the 228th item was just $5. So again, this exercise of flipping back and forth between regular revenue versus marginal revenue, regular cost versus marginal cost, thinking the full revenue and cost of all 228 items versus the marginal revenue and cost of just the 228th item. Okay, and finally, let's do profit. What is the regular and marginal profit for 228 items? So first of all, what's the formula for profit? P of Q is equal to?
Revenue minus cost.
Yeah, revenue minus cost. So we have all revenue minus all cost. So that's our profit formula. Profit is always revenue minus cost. And in this particular case, we have quite the formula to figure out. So revenue was negative 1.25 Q squared plus 290 Q minus the cost, which was 5Q plus 6,000. And that will be our full profit for however many items that we wish to see. Now, folks, my biggest dilemma right now is that I didn't give you enough room on your paper. You're probably really cramming to get all this in. I'll definitely make the spacing better should I put this problem on the final. So what is our formula for profit? The profit for Q items is what? Negative 1.25 Q squared. And then we're distributing this minus sign. So 290Q minus 5Q is plus 285Q. And then minus 6,000. So that's our profit. So how much profit did we get from 228 items? First of all, do we already know the answer? Because we already know the revenue and the cost from 228 items. So what should our answer be? The answer should be 1140 minus 7140. Our answer should be negative $6,000. And now if we actually plug that in, the value of 228, that'd be negative 1.25 times 228 squared plus 285 times 228 minus 6,000. And yes, indeed, it's negative 6,000. So we're $6,000 in the hole from selling these 228 items. And that's the same value that we would have gotten had we just taken the revenue and we subtracted them. So what's our marginal profit? How do we find our marginal profit? How do we find marginal profit? Take the derivative. So that'll be negative 2.5Q plus 285. And so the marginal profit of the 228th item. Now, by the way, should we also know this? What will our marginal profit be from the 228th item? If we go ahead and subtract marginal revenue minus marginal cost, that'd be negative 280 minus 5. So what should the answer be? What is it? Negative 280 minus 5? It should be negative 285. Well, let's find out. If we plug in negative 2.5 times 228 plus 285, indeed, the answer is negative 285. So overall, we've lost $6,000 from selling 228 items. But how much money did I lose just by making the 228th item? $285. So even though overall we've lost $6,000 from this venture, that 228th item alone lost me almost $300. Now, folks, how's this business going? This business is not very good. What's the problem? Like, how many items should we make for this business to be profitable? How many items should we make for this business to be profitable? What would we want to do? We would want to maximize profit, right? Well, where's the maximum of profit? What's our profit formula? Negative, what was our profit formula? Negative 1.25 q squared plus 285x minus 6,000. Here's our profit formula. Can you guys see the graph? Where's the maximum profit? Right there. How many items are being sold to maximize profit? 114. And in fact, what's the relationship between the number 228 and 114? Yeah, half. So selling 228 items, that's terrible. That puts us just past a positive profit. If you'll notice, 228 is down here where profit is negative. That means we've sold way too many items and that we should have stopped a long time ago and only sold 114 items. Now, folks, how can we use calculus to solve that the profit maximum was at 114? One more problem to do here. How could we have figured out where the maximum profit is? Like if this is my graph of profit, how do you find the maximum? Yeah, take the derivative and set it equal to 0. Well, here's my derivative formula. And so I'm going to set that equal to 0. And so that gives me negative 2.5q plus 285 equals 0. So I move the 285 over to the right. And I get negative 2.5q equals negative 285. And then I go ahead and divide by negative 2.5. And that gives us, presumably, 114. Presumably because I didn't divide it yet, but 285 divided by 2.5, yes, is 114. So we would advise this company to not sell that many products, that they should really only be selling around 114. And then what? Should they sell 115? If somebody called them up and said, I know you're done doing business for the year, but will you please sell me 115th item? Should they sell the 115th item? Theoretically, no. They should send them away. They should say, sorry, I'm done for the year. Can you even imagine if you were done working for the year? You know, everyone's like, it's December. I'm done working for the year. Your job calls you up. They're like, Nick, get in here, man. We need you to work. You're like, I'm done working for the year. If I work any more this year, I'm gonna lose profit. Okay, well, folks, my phone just went off a second ago. Let's just see where we are. We're now about to start a review of the derivative formulas. So 18, 19, 20, those are derivative formulas. 21, more derivative, product rule, quotient rule, chain rule. And then, yeah, a couple other applications. How far does this go? We still have quite a bit of derivative review to do. But we'll just keep on going and see how far we get. So we're on number 18, but let's take a quick break. So the time is 11:05. Let's start up again at 11:15.
A ver si vamos a acabar con la clase el miércoles y ya no nos presentáramos. ¿Sí? ¿Sí? ¿No lo he recibido? ¿Ya te dice? Ya te dice. Dijo que en 2 horas nos lo mandaban, o como a las 2 nos iba a mandar y no, ayer. No lo he recibido. By the way, may I have my practice test?
Yeah, I'm gonna pass it all back in the class.
So básicamente acabamos de ver. Está bien. Estaba mirando mis grados. Me mandó este no. Porque yo mandé uno que no lo mandé. Y luego me mandó este. No sé qué doblan las uñas de ahorita. Ya que se empieza a doblar. Las publications. Que me mandó para nosotros. Y ustedes. Creo que voy a pasar los últimos aquí. También se acabó eso. Están mirando mis lados. Ustedes tengo. ¿Qué agarraste aquí? Ay, me acuerdo. Yo estoy a un punto para tener. ¿Sí? Yo no. ¿Tú qué agarraste aquí? 70. ¿Sí? Yo 40 y algo. ¿En serio? Santo cielo. ¿Te dije? Si yo sí me estaba comiendo las uñas, dije, oh my god, I can't do it. Y le dije, oh my god, I did so good in my math test. I was so worried. Y no. Por eso así que estudié bien. I checked my grade yesterday and I was like, yay. I didn't do as bad as I thought I would. So, en las otras, nomás, la única que me tengo que preocupar es la contabilidad. So, if I don't come, like, after Wednesday, once we take the test, we're done in tax class, and I'm good, because all I have to do is focus on math, and, no, porque math is awesome. Nomás matemáticas y accounting, and that's all. We won't have to show up to the tax class either, to Excel either. Dijo que en Excel, nos iba a dejar salir solamente, iba a ver los lados de las demás personas, si necesitan ayuda de las demás personas. Pues.
That's the link that says first day. So you click on that, it'll tell you what to do.
Yes, there's the final. Pero el final va a ser, the 10 key. Va a querer que hagamos graph y todas esas cosas. ¿Qué?
Con las uñas no puedo hacer bien el 10 key.
Or something that catches your eye. Es que dijo que si es algo que puedes usar para tu vida actual. I was thinking about it, I was like, I really don't have anything to use it for.
Okay.
No lo puedo usar para el mandado, no lo puedo usar para... No mire el uso. So I'm going to use the 10 key one. It's just going to be easier. Yeah, it's just going to be easier. Hicimos 10 key for 10 minutes yesterday. Use 10 key for 10 minutes. I have to do my en accounting sí estoy como a 4 puntos para tener una C. ¿Te acuerdas que esa tarea no me dejó hacerla si no tuviera una C? Nomás que esa tarea que me dijo que le iba a tener a hacer fin del día y no me permitió hacerlo, ya nunca me la volví a hacer. Aunque se la pedí. Pero de cualquier manera, si hago eso, voy a tener que voy a estar bien. No, en este estoy a punto de tener. Estoy haciendo toda para la contabilidad, estoy haciendo todos los extras. Sí, no, ajá. Porque el último test nomás en accounting es donde. Y si lo paso de panzazo con un 70. Estoy ahí, pero no estoy. No lo pensé. Yeah. multiplication years. Because it's 9 days after, or it goes away after the first.
Oh, so you're getting Christmas and New Year's?
Yeah, and he has vacation and stuff. Like this is just got that to my friend texted me last night. I was like, oh.
From the 22nd to the 20th.
Where are they celebrating at home? It's just not for the kids, so we're thinking about.
We used to go up north to the mall and have the kids do slide in those plastic slides for the day. That's what we do.
I don't know much about the mountains.
Go up.
First.
I know, right?
Everything.
I mean, hour and a half there. Slide, stop by at Denny's or whatever, have dinner, go back and.
It's ENH, that's why. Not EN. Yeah, most of them. We took them to Heavy Marketplace, because on Saturday they did the snow. And he's just doing it around and you get so sad in the snow when he's like, every time.
So, you know, if you get snow for the day and no feel like
I
a
didn't
whole,
even
like
read
a
the
heating
book.
pad.
I was supposed to reference what you guys know. No, I didn't, and I got a 96.
Well, I just think about it, it is the whole, like, you're gonna slide.
That's true.
But,
That's pretty.
it's pretty awesome.
All right, folks. Let's go and keep on going. These next couple problems are a pretty basic review of taking a derivative, which I think for the most part, this will feel pretty comfortable now. So how about the first one, number 18? What's the derivative of negative 5x to the 10th minus 9x to the 5th? How do we do the power rule? We've been doing anti-power rule for so long. It's good to review. How do you do the power rule? Yeah, you multiply the exponent. So you drop the exponent down in front, and you're multiplying, so that'd be negative 50x to the, and what do you do?
9.
You subtract 1 to become 9.
Yeah.
And then you do the same thing, so you bring that 5 down up front and multiply it times the negative 9, which is negative 45, and then you subtract 1, x to the 4th. Just the whole final?
Just skip chapter 3 all together.
Okay. Well, I'll consider that, Julie.
Like minus negative.
Where?
Because there's already a minus sign. So I was just-
Right, you wouldn't put minus negative because technically what you have here, if you want to think of it another way, you can think of it as though you're operating right there. So 5 times 9 is 45, and then x to the 4th, and that minus sign is still there. Yeah, good question. Okay, what about the derivative of 2 natural log of x? Notice there's 2 parts to this, the 2 and the natural log of x. The 2 is simply a,
It just comes along.
yeah, it's just a coefficient. It just comes along for the ride. So what's the derivative of natural log of x? 1 over x. So it's 2 times 1 over x, which you can write more simply as 2 over x. Yeah, the 2 just comes along for the ride. The derivative of natural log is 1 over x. This next one has multiple components, 3 root x minus 4 over x to the 3rd. And this problem is to remind you that in order to do the power rule, you have to rewrite your variable as being in the numerator with an exponent. So,
like 3x to the negative 1/2.
well, this is in the numerator. It's just a normal
So it's
square root.
positive one.
Now, positive 1/2, and then 4x to the negative 3. Yeah, so this was just a regular 1/2 because the square root's already in the numerator. It doesn't have to move to the numerator. But this x cubed was in the denominator. It has to move to the numerator, so it becomes negative 3. And now you can actually do the power rule. So again, in the power rule, you multiply the exponent towards the front.
Is that a nut of 3 x? 3 over 2 x?
Yeah, that's 3x to the 1/2. Wait, what? Oh, you're asking what happens when you multiply? Well, you're going to have 1/2 times 3. X to the 1/2 minus 1 is negative 1/2. And then what's 1/2 of 3?
3.
Yeah, 3 halves or 1.5. You could call it 3 halves or 1.5, your choice. And then, although I guess the 3 halves would look better, Julie. I like your idea, 3 halves. And then now, Clarissa, go back to your question. This is a negative 3 times a negative 4. So that's going to be a positive 12. Yeah, and then you subtract 1, negative 3 minus 1, negative 4. So now we need to make all that look better. by doing those negative exponents. And so you push both of those you push both of those x's into the denominator. So the first term you have 3 over 2 x to the 1/2. And then this one is 12 over x to the 4th.
Can you just jump right into 23 to the over 2 square root? Or do you want to?
Yeah. Oh, you could just jump right into calling that the square root of x. Is that what you're asking?
Yeah.
Yeah. This is a really nice and clean final answer. That's a really nice and clean final answer because it looks like the original. The original was using square roots and it had positive exponents. And that's what you want in your answer. You want square roots and positive exponents. It's kind of funny that we want answers to be presented in terms of square roots and positive exponents, but in order to actually do calculus, you can't have square roots and positive exponents. You actually need negative exponents and raising something to the 1/2. So that's kind of ironic. Why don't we just live our life here? You know, if this is where we do the calculus, why don't we live our life there? Why do we even bother writing it like this? Huh?
So 3 over 2 is because, oh, so you just put it back to the 1/2 to the regular.
Yeah, I put the 1/2 becomes the square root, and because it's negative, it goes in the denominator. Yeah, in fact, everybody, good question. 3/2 x to the 1/2, what would that look like? And 3/2 x to the negative 1/2, what does that look like? So here, you've got 3 over 2, and since x to the 1/2 is positive, or it's a positive 1/2, that square root of x goes in the numerator. Whereas over here, you've got 3 over 2, and this x to the 1/2 is negative, so that square root goes in the denominator. Is that helpful to see both of them?
Yeah.
That's the difference between them.
I was trying to figure out what I was doing.
You did?
Yeah.
Nice.
Because every time I brought the 3 over 2 over, I would just put x instead of bringing it in.
Ah, okay. Okay, Mom, does that answer your question about where the square root of x goes? Yeah. Okay. Well, let's keep going. Now this next one, I'm forgetting if I think we did do a couple of these. So let's just go ahead and try it out. It says, if the function is a parabola. So everybody go ahead and just make a quick graph and draw a parabola. I don't even, may not even care what it looks like, but just draw a parabola. And they're saying, find the slope at -2. So, oh, well, gosh. If we're going to do this problem, we should make it accurate. What does 3x squared?
For this question, can we just cross out?
What?
For this question, can we just cross out?
No,
Because
no.
other practice that you cross out, and then you promise us that we will not put it on the test, so we cross
Wait,
out.
where? On what practice?
You promise that we did not force you to promise.
Wait, what? I said what? Are you sure, Carmen? What is that?
Yes.
That's the what practice test?
He said that about chapter 3 of Albert.
No,
Yeah, right.
chapter 2A practice test.
Oh, that was the 2A practice test, and I told you to skip it.
Yeah.
Gosh, how did Carmen have that at the ready, folks? Seriously?
Because I just do ahead.
I had the same thing in my type too.
What, that we skipped it?
Yeah.
All right, cross it out, folks.
And 23 also.
No. 23 is a good question. You just made that up.
Same question.
Nope. 23 is a good question. We're going to do that. 23 is a necessary question. Honestly, so is 21, but if we didn't previously study it, it's hardly fair to put it on the final. So that's the only reason I'm agreeing. 23, great question. Now, way to go, Carmen. I feel a little beat down. I feel like I just got mugged in a dark alley. All right. Now, this graph, which is cubic, has 2 horizontal tangents. Let's look at it real quick. As always, now you all have graphing calculators, right? I hope you all have graphing calculators. I'll bring a couple extra just in case you need one. But see, during the test, you'd want to immediately graph everything they give you just so you have an idea of what it looks like. So here's this particular graph, and there, you can see what it looks like. Well, kind of. Let's make that look better. So that's 20 and 20. Ah, what a nice graph. Look at this. So what does the question say? The graph of blank has 2 horizontal tangents. Where are they? Everyone draw a picture of this. The graph. What do you want, Julie? Okay. So go ahead and draw a picture of the graph. It goes through the origin. Well, it looks like it goes through the origin, and it looks like this. Right? It doesn't actually go through the origin. It appears to cross through at the vertical intercept of 6. In any case, that's what the graph looks like. And they're saying that it has 2 horizontal tangents. So one of the horizontal tangents is here, and the other horizontal tangent is here. Okay? So that's why it's so important to graph this. When you're sitting there taking the test, get out your graphing calculator, look at what it looks like so you can actually imagine and know what we're talking about. The graph of this function has 2 horizontal tangents. One occurs at a negative value of x, which is this one, and one occurs at a positive value of x, which is this one. Find the location of the horizontal tangents. So how do I find those x values? Yeah, you take the derivative and set it equal to 0. Because the one thing you know for sure is that the derivative is 0 there and there. So we take the derivative, so f prime of x is equal to what? The derivative is?
6.
What?
6x squared plus 18.
Oh yeah, 6x squared plus 18x minus 108. All right, so that's the derivative. And we're wondering, when is that equal to 0? So you see what I did? I found the derivative, and then I went ahead and took that and set it equal to 0. And that's what we're going to solve. What's the first thing we could do to make our life better? Yeah, divide out a 6. So everything gets divided by 6. So now we have x squared plus 3x minus what? 18? And now you can do this however you like. You can do the quadratic formula if you want to do negative b plus or minus square root of b squared minus 4ac all over 2a. Or you can just factor. What multiplies to make negative 18 that adds to make 3? That's it.
Thank you.
Yeah, either 2 and 9 or 3 and 6. It looks like it's 3 and 6. Which one's positive? Which one's negative?
6 is positive.
Yeah, 6 is positive, 3 is negative. And therefore, what are my values? Each of those gets sets equal to 0, right?
Negative 6, positive 3.
Yeah. So x plus 6 is 0 or x minus 3 is 0, which tells us either x is negative 6 or x is equal to 3. And see, now that you have a graph, it's so nice that you can just put that in there. So that's my negative 6, this is my positive 3, and that's the location of my horizontal tangents. Now, to be fair, it says find the location of the horizontal tangents. That is the x value of the horizontal tangent, but the actual location is a coordinate. So where's that coordinate and where's that coordinate? Yeah, you take the 3 and the negative 6 and you plug it back into the original, right? So now we'll go ahead and say, what's f of negative 6 and what's f of 3? So now you would want to have already plugged that into your calculator, because if it were already in your calculator, you could just use the graphing calculator feature to find those really quickly without having to plug it all in. So like 2x cubed plus 9x squared minus 108x plus 6. And then once you graph it, you can use your second calc feature to find the value of negative 6. Oh no, it didn't do it. That's okay, I'm going to use my table. So the location at negative 6 is 546. And the location at 3 is negative 183. There, good, that makes sense. So my coordinate up here is the coordinate negative 6, 546. And my coordinate down here is 3, negative 183. Folks, I definitely am putting a problem like this on the test. And your answer should be this. That's a really nice answer. Isn't that a nice answer? That's a really good answer to this problem. The question says the graph of f of x has 2 horizontal tangents, one at a negative value of x, one at a positive value of x. Find the location of the horizontal tangents. This picture really makes it pop. Like there's no doubt in the reader's mind where those horizontal tangents are because they can see it so visually and clearly. So your final answer should be coordinates, and there should be a little sketch because that looks good. That looks really good. Yeah, in fact, I would say this is one of the best kind of bread and butter problems of calculus, is being able to solve a problem like this. Questions about it? Okay, the next one is the product rule. How do we use the product rule? Maybe we should write down the product rule first. What's the derivative of f times g? Remember writing down the formula? The derivative of f times g is the derivative of the first times the second plus the derivative of the second times the first. Is that how we wrote it out a long, long time ago? Or did we write it out differently?
I think that's how we did it.
I mean, I suppose we could have written it out with f of x and g of x. The derivative of f of x times g of x is the derivative of the first times the second plus the derivative of the second times the first. Either way, however you write it down, both of those are a nice way of writing it down. The key is that you remember verbally how to say it. Derivative of the first times the second plus derivative of the second times the first. And you'll notice that it's addition because the quotient rule is subtraction. But the product rule is addition. So, in this particular case, our product is t squared plus 7t plus 7 times 7t squared plus 6. And we want to find the derivative of all that. So what will it be? The derivative of the first, which is what?
2t plus 7.
Yeah, 2t plus 7, times the second, which is 7t squared plus 6, plus the derivative of the second, which is, yeah, just 14t, times the first, which is t squared plus 7t plus 7. Folks, I'm telling you that that's perfectly fine just to leave it like that. For the sake of the final exam, you can just implement the product rule and I will look at it. Because from here on in, I mean, that's just standard algebra to sit there and plug and chug and FOIL and distribute. You know, that's just more time and energy. The key thing is I want to know that you know how to do the product rule. Plus, if you were going to do all that FOIL business, when should you have done the FOIL business? Right up front. Had you done it right up front, you wouldn't have even had to do the product rule because it would just be one long polynomial and you would just take the derivative. So let's just leave it like that. Is everyone okay with that?
Mm-hmm.
Okay. Carmen didn't even have to threaten me. All right. The next one is the quotient rule. How does the quotient rule work? Wait. Did I skip one? I did skip one.
25.
Yeah, there's another product rule up at the top. So 25. So now our product is what? X squared plus x minus 3
Yes.
times e to the x. Okay, so same product rule. We want to take the derivative of that product. So what's the derivative of the first? 2x plus 1 times the second plus the derivative of the second, which is just itself, the derivative of e to the x is e to the x, times the first. Now, I could say the same thing. I could say, well, folks, you know, there's no need to, you know, FOIL all this stuff out. But there's nothing to FOIL here. Here, I do want you to go one step further. How do we simplify this? You just pull the e to the x out, right? Because then that leaves you behind with 2x plus 1 plus x squared plus x minus 3. And this is just a matter of combining like terms. So it's e to the x times x squared plus 3x minus 2. That's well worth the time and energy. So I would like you to simplify something like that. Okay, how does the quotient rule work? Who remembers the formula? So we're going to take the derivative of f over g. Ho
Cody high.
d high,
Over Heidi.
yeah, minus high d ho
All over home.
all over ho. Yeah, exactly right. So ho d high minus high d ho all over ho ho. And you'll notice that this looks like the product rule. At least the numerator looks like the product rule, except it's subtraction instead of addition. And it has to be ho d high all over g squared. All right, so let's do that. So it's going to be a lot of parentheses, right? Lots of parentheses. So ho, that's 2 plus x squared. D high, what's the derivative of the top?
Negative 2.
Yeah, negative 2x. So ho d high minus high d ho. What's the derivative of the bottom? Yeah, just 2x. All over ho ho, which is 2 plus x squared. Now right here you might say, well, you know, can't we just leave it there? That's just a lot of multiplication. But can we not do the same thing as we did with e to the x? What could we factor out of the top? Well, the 2 plus x squared and the 2 minus x squared are different, but the 2x we could factor out. So if I brought a 2x out in front, then what I'd have left behind is, that's a negative 1 still. So I'd have negative 1 times 2 plus x squared. And then over here, I just have minus 2 minus x squared.
Didn't you forget the squared on the bottom?
Oh, I did forget the squared on the bottom. Thank you. I'm not going to do anything with the bottom, but thank you. I did forget the squared. Yeah, because that was ho-ho. So now that I took out that 2x, what is going to happen in the top? At this point, we're just combining like terms, right? And we do get to combine some really wonderful terms in the top because we have negative 2 minus x squared minus 2 plus x squared. Now what happens? What happens in the numerator? What happens to the x squared terms? Yeah, they cancel out. Well, that's very convenient. So now that's negative 2 minus 2. That's negative 4. So I have 2x, oops, 2x times negative 4 in the top, and the 2 plus x squared squared on the bottom. And now we simplify out to a very nice answer of negative 8x over 2 plus x squared squared. All right. You'll have probably one product rule, one quotient rule on the final, and then you'll have a chain rule. So how did we say the chain rule? What's the formula? We start with f of g of x, and we want to take the derivative of that. So how does it work? The chain rule, you do the derivative of the outside, leaving the inside alone, and then multiply by the derivative of the inside. So let's look at that. You take the derivative of the outside, so that's f prime, leaving the inside alone of g of x, and then you multiply by the derivative of the inside. None of you have even asked if there's a formula sheet for the final exam.
Is there a formula sheet for that?
I don't know. I wasn't considering it. What, Carmen?
Because you gave us.
Yeah, I don't know. I mean, should I give you formulas?
Yes, for sure.
I mean, would that be relevant? Or I'll consider it. Let me think. Why don't you all, for your homework tonight, come back to class on Thursday with a list of formulas you want to be able to see on the test? Okay, that requires a little effort from your part. You got to go home, look at all the formulas, look at what we've done, and say, these are the formulas I want to have access to on the test. And then I'll consider that, and I'll give you some of them. That way you'll know which ones you need to memorize and which ones I'll let you see. So everyone think about that. Okay, so what will be our chain rule for this? What's the outside function? And it might be helpful if you have, well, I don't know if you have different colors, but our function on the, what's the 5? Is that an outside or an inside function?
Outside the 5.
But what is the 5? The 5 is just a, it's just a coefficient, so it's just coming along. What's the outside function? Yeah, something to the 19th. And what's the inside function?
7x.
Yeah, 7x to the 4th plus 5x cubed. So that's important that we identify what's what. So my 5 is just a coefficient coming along for the ride. The outside function is to the 19th, and the inside function is 7x to the 4th plus 5x cubed. So now, how do we do the chain rule? We take the derivative of the outside function, so that's going to be 19 times 5 to the 18th. There, I just did the derivative of the outside. I didn't multiply the 19 times the 5 yet, I just made a note that I'm going to multiply them. So I did the derivative of the outside function, and what do I do to the inside? Leave it alone. And then what do we do? Multiply by the derivative of the inside. No, it's a little better. And the derivative of the inside is?
28x to the 3rd plus 15x squared.
Yeah. Now, is there anything to simplify here? Well, no, not really, because this thing is being raised to the 18th power. We can't multiply those two together, so that's just done. The only thing we need to do is simplify the 19 times 5. So 19 times 5 is?
95.
95. So it's just 95 parenthesis 7x to the 4th plus 5x cubed to the 18th times 28x cubed plus 15x squared. So there's not a lot to simplify in the chain rule. With the chain rule, you really won't have to simplify much. You're just going to write it down. Now, folks, on the fly here, could we now take the integral of 95 7x to the 4th plus 5x cubed to the 18th times 28x cubed plus 15x squared dx? Could we take that integral?
No.
We could, because to take the integral, we just take the antiderivative. And what's the antiderivative of all this? Just this, right? That's the antiderivative. So how would we do it? You would use substitution. What would our u be? Remember, the u is the inside function. What's the insidemost function? What was the inside function? This is to the 18th, so the inside function is this. So our u would be 7x to the 4th plus 5x cubed. And we know that's a good choice of u because du, which is 28x cubed plus 15x squared dx, is right there. So we definitely have the u part and the du part. And this 95 I can just bring out front. There, it's not even there. I'll bring it out front. So now how do I replace that with my u? This is really 95 times the integral of what? U to the 18th du. Right? So there's a u substitution. Going directly backwards, what's the integral of u to the 18th? What's the anti-power rule? You add 1 and then divide by the resulting coefficient. And that's it. And so what is 95 divided by 19? We should all know. 5. So that's 5u to the 19th. And what is u again? 7x to the 4th plus 5x cubed, the 19th. Is that the original problem? 5 times 7x to the 4th plus 5x cubed to the 19th? That is the original problem. So what is u substitution? It's running the chain rule backwards. Somebody asks you, what's u substitution? U substitution is doing the chain rule backwards. And that's u substitution. That wasn't as bad as y'all thought, was it? I mean, didn't that clean up real nice? It just became u to the 18th du. That was very nice. Very nice and clean. Okay, let's do another chain rule.
Before the test, you just need to do this part.
Yeah, for this test, yeah, for that question, you just take the derivative. Yeah, but I thought that was appropriate to show real quick. U substitution is just undoing the derivative. Okay, so what about this chain rule? We have 3. What's the 3? Is that the inside or the outside function? Neither. It's the coefficient. The coefficient just comes along for the ride. But then you have e to the, and what's e to the? The e to the is the outside function. And what's the inside function? 3x to the 4th plus 9x to the 9th. Now you know 3x to the 4th plus 9x to the 9th is the inside function because it's literally inside, right? It's inside the exponent of e to the. Okay, so now how do we take the derivative of this? How does the chain rule work again? You take the derivative of the outside function, and what's the derivative of e to the? The derivative of e to the is e to the. So far the derivative, let me take the derivative here, is 3 e to the, and you leave the inside alone, so 3x to the 4th plus 9x to the 9th, times what? The derivative of the inside function, which is what? 12x cubed plus 81 x to the 8th. Now, notice what's very important here is this parenthesis is in the exponent. It's a superscript. Please, please, when you're writing down your answer, it should not look like this. Right? What is that? Yeah, that's wrong and sloppy because you can't distinguish what's the exponent and what's being multiplied. So when you show an exponent on e, it's really, it should be nice and small and tiny. That. To distinguish it from the fact that you're now multiplying it times that parenthetical. All right. Okay, so there's a chain rule. Let's do a couple more chain rules before we go. We got, actually there's 2 more chain rules. Yeah, there's 2 more chain rules. Let's just do one more chain rule, then I said my last 5 minutes would be announcements, and I'll pass back tests. So one more chain rule. How do you do the chain rule of natural log? Isn't that what the next one is? So our function is the natural log.
X squared plus 8x plus 25.
Yeah. Great. So what's the derivative of natural log of x? Just 1 over x. So the derivative would be 1 over the argument, because the derivative of natural log of x is 1 over x. The derivative of natural log of the argument is 1 over the argument. So it's simply 1 over x squared plus 8x plus 25. But here the inside function was x squared plus 8x plus 25. So you do 1 over the argument, leaving the argument alone, and then multiply by the derivative of the inside. And what's the derivative of the inside?
2x.
Yeah, 2x plus 8. And how do you make that clean up and look good? You put the 2x plus 8 in the numerator, and you leave the x squared plus 8x plus 25 in the denominator. All right. Well, for next class, as far as the derivative review, which we didn't quite finish today, okay, well, you know, there's not that much left. I might choose some of those for us to skip. Hopefully you'll be okay with that. And then we'll be able to move in and do the integral review. Now here's the key thing. I'm about to give you back your integral test. And a lot of these questions are very similar to the integral test. So when I graded your tests, I wrote a lot of feedback on your test, showing you how to start the problem and showing you some correct steps. And if you did most of the problem wrong and you had an error, I pointed out your error. So you should be able to look at your own test and see what you did and figure out your own mistakes. So your homework for next class, folks, you have 2 pieces of homework for next class. One is review your own exam. You should be able to figure out a lot of your mistakes by just reviewing your own exam before you come to class next time. And then 2, think about a formula sheet. Think about a formula sheet. Okay? Other than that, next class we're going to review integrals, which is basically reviewing what your exam was. You might want to come in and see me during office hours to review your integral test so that we can point that out. Okay, so announcements, and before I pass this back. The first thing I want you all to know is that I went through the grade book and I calculated that every single person in here can pass the class, which to me is great. I like to know that everyone is going to pass the class and move on to next semester, because in order to enroll in your class next semester, you have to pass this class. So everyone can pass the class. But some of you need to go on to Math AS and finish your homework. Okay, some of you have homework assignments that you've not finished. So in order to pass the class, you do need to go back in and finish that homework. And I'm happy to help you with that. So we have exactly 2 weeks left, folks. When is the last day to turn anything in? December 15th. Okay, Friday, December 15th is your last day to submit homework to me, and that is Math AS. So everyone keep that in mind, that that's your ultimate due date. Okay, here's your tests. What in there? Clarissa, Daisy, Susanna, Thomas is not here. Yeah. And Rose is right there. Carmen. Me. 1 second, folks. I have one more thing. I'm passing out your practice test. Thank you. Carmen. Mom. Julie. Rose Thomas. Okay. Okay. Does class really end at 11:50? Okay. Thank you, folks.
No, I